You turn on a lamp and instantly the room fills with light. But what is that light? Where did it come from and how did it get here so fast? For centuries, humans have wondered, is light a wave, a particle, a stream of energy? The truth is more astonishing than fiction. Light doesn't just travel, it defines travel. It sets the cosmic speed limit. It bends time. It reveals the universe's deepest secrets. So let's follow a single photon from its birth in the sun to the moment it strikes your eye. This is the journey of light. Light is electromagnetic radiation, a self-propagating wave of electric and magnetic fields oscillating perpendicular to each other, racing through space. But it's also made of particles called photons, massless packets of pure energy. This duality isn't a contradiction, it's the heart of quantum reality. When light behaves like a wave, it interferes, diffracts, and spreads. When it acts like a particle, it hits like a bullet, one photon at a time. Both are true. Light is neither wave nor particle alone. It's something deeper, a quantum object that reveals itself differently depending on how we look. In a vacuum, light travels at 299,792,458 meters per second, denoted as c. That's 186,000 miles per second, fast enough to circle Earth 75 times in 1 second. Nothing with mass can reach this speed. Why? Because as you accelerate, your mass increases, demanding infinite energy to hit c. But light has no mass, so it doesn't accelerate. It's born at full speed. The moment an electron drops to a lower energy level in an atom, poof, a photon is emitted already moving at c. No ramp up, no delay, just there and gone. In empty space, light flies unimpeded, but when it enters air, water, or glass, it slows down. Not because photons lose energy, but because they're absorbed and re-emitted by atoms in the material. Each interaction takes a tiny fraction of time. The result? Light appears to slow to 0.75 of c in water, 0.6 in glass. This slowing causes refraction, the bending of light that makes straws look broken in water. Yet between atoms, photons still move at c. The slowing is an illusion of the crowd. Light travels in straight lines, called rays. That's why shadows have sharp edges in direct sunlight. But light isn't perfectly straight at tiny scales. It spreads due to diffraction. Shine light through a pinhole and it fans out. This proves light is a wave. Yet over large distances, like from the sun to Earth, rays stay nearly parallel. That's why eclipses cast crisp shadows. Light's straightness lets us build cameras, telescopes, and laser pointers. But its hidden waviness, that's how we see rainbows. When light hits a smooth surface like a mirror, it reflects. The angle it hits equals the angle it bounces. Simple. But why? Because the electric field of the light wave jiggles electrons in the metal, which then re-radiate a new wave backward. Polished silver or aluminum does this perfectly. Rough surfaces scatter light in all directions. That's diffuse reflection. Why paper isn't shiny. But mirrors, they preserve the image, because every ray bounces predictably. You see yourself not because light bounces off you, but because your face sends light to the mirror, which sends it back to your eyes. When light crosses from air to water, it bends. This is refraction. It happens because one part of the wavefront hits the water first and slows down, while the other part is still in air, moving faster. The wave pivots. Lenses use this to focus light. A convex lens bends rays inward to a point, the focal point. That's how your eye works. Your cornea and lens refract light onto the retina. Without refraction, glasses, microscopes, and Hubble wouldn't exist. Even raindrops refract sunlight, splitting it into colors. That's a rainbow. White light isn't pure. It's a mix of all colors, each with a different wavelength. Blue light has short waves, red has long ones. When white light enters a prism, blue slows more than red, so it bends more. This dispersion spreads light into a spectrum. Rainbows work the same way. Sunlight enters a raindrop, reflects off the back, and exits, refracting twice. The result? A circular arc of color. You only see part of it because the ground blocks the rest, but from a plane you can see the full circle. Nature's perfect prism. Why is the sky blue? Because of Rayleigh scattering. Sunlight hits molecules in the air, mostly nitrogen and oxygen. Shorter wavelengths, blue-violet, scatter 16x more than longer ones, red. So blue light bounces all over the sky, reaching your eyes from every direction. At sunset, sunlight passes through more atmosphere. Most blue is scattered away, leaving reds and oranges. That's why sunsets glow. Without scattering, the sky would be black even at noon, like on the moon. Light waves usually vibrate in all directions, but when reflected or filtered, they can align, becoming polarized. Sunglasses use polarizing filters to block horizontally vibrating glare from roads or water. Bees use polarization to navigate. LCD screens emit polarized light. That's why your phone looks dark through some sunglasses. Polarization proves light is a transverse wave, vibrating sideways, not forward. It's invisible to us, but everywhere. Every photon carries a story. Its color tells us an atom's energy jump, its direction reveals where it came from, its polarization hints at magnetic fields. Astronomers decode starlight to learn a star's composition, temperature, motion, and age. When light from a distant galaxy is redshifted, we know the universe is expanding. Light isn't just illumination, it's cosmic messenger. The oldest light we see is the cosmic microwave background, a faint glow from 380,000 years after the Big Bang. We're literally seeing the infant universe. At the quantum level, light gets strange. In the double-slit experiment, a single photon passes through two slits at once, interfering with itself like a wave. But if you try to watch which slit it uses, it acts like a particle. The act of observation changes the outcome. Light exists in a superposition of paths until measured. This isn't theory, it's lab fact. Photons don't have definite paths. They explore all possible routes, and the probabilities add up to create the patterns we see. Reality is probabilistic. Light shows us that. Einstein realized if light's speed is constant for all observers, then time and space must bend. If you chase a light beam at half c, you'd expect it to crawl away at half speed. But no, it still races off at c. How? Your clock slows, your ruler shrinks, time dilates, length contracts. Light enforces cosmic order. GPS satellites must correct for this. Their clocks run faster in orbit than on Earth. Without relativity, your phone's map would be off by miles. Light doesn't just travel through space-time, it shapes it. From the core of the sun, a photon takes 100,000 years to reach the surface, bouncing between atoms in a random walk. But once free, it covers the 93 million miles to Earth in 8 minutes and 20 seconds. Starlight we see tonight may be from stars already dead. The Andromeda Galaxy, its light left when early humans walked Earth. Telescopes are time machines. The James Webb Telescope sees galaxies as they were 13.5 billion years ago, just 400 million years after the Big Bang. Light connects us to the past. Your eyes catch light. Photons enter through the cornea, focus via the lens, and strike the retina. There, rods detect brightness, cones detect color, red, green, blue. Each photon absorbed triggers a chemical signal to your brain. You need just 5 to 9 photons to see a flash in total darkness. But you don't see light traveling, you see where it stops. A laser beam is invisible in vacuum. You only see it when dust scatters light to your eyes. Vision isn't passive reception, it's active interpretation. Your brain constructs reality from light's echoes. We now manipulate light with insane precision. Lasers amplify light into coherent beams, used in surgery, manufacturing, and fiber optics. Quantum entanglement links photons across distance, enabling unhackable communication. Metamaterials bend light backward, creating invisibility cloaks, and optical computing may replace electrons with photons for faster processing. Light is no longer just observed, it's engineered. The next revolution won't be powered by electricity, but by light. So the next time you flip a switch, remember you're not just lighting a room, you're unleashing trillions of photons, born in a wire, racing at the universe's speed limit, carrying energy, information, and wonder. Light doesn't just show us the world, it is the world's messenger, and its journey never truly ends.